everyone, welcome to Gate Pass. So in this video I am going to take the remaining two problems on thermodynamics which appeared in Gate 2020. So the problem which we are going to take is based on the chemical reaction equilibrium. So here your N2O4 is decomposing into NO2 in a isothermal and a isobaric reactor which is maintained at 298 Kelvin and 1 bar pressure. Now the standard Gibbs free energy change of reaction is given as 5253 joules per mole. All other things have been given which we will discuss later on. Whatever the assumptions which are given we will discuss when we solve the problem. And they have said that initially 1 mole of N2O4 is charged to the reactor. Now you have to find out at equilibrium what is the fraction of N2O4 that decomposes. So there are 4 options which are given and you have to find out which one is the correct one. Okay, so as usual we will start with the concepts. So you all know that the criteria of chemical reaction equilibrium is summation of mu I that is equal to 0. Okay, so summation mu I that is equal to 0, when mu I is nothing but your stoichiometric coefficients and mu I are your chemical potentials. But usually what we do is we change mu I into fugacities. So when you use those definitions and then change it, so your final equation then takes the form of, so this is product over all I Fi cap upon Fi naught, that is raised to mu I. Okay, I should make this bigger arrow. Oh sorry, bigger bracket. That is equal to exponent of minus delta G0 by RT. Okay. So starting from here, put the definitions of fugacities, replace chemical potential by fugacities, and then you end up with this equation. Okay. In this case, as I have told you, the delta G0 is the standard Gibbs free energy change of reaction, and this fugacity, this is the fugacity of species I at the standard state. So let's first see what do you mean by standard state. So we define standard state as the state of pure species which is at the system temperature but at a pressure which is taken as 1 bar. Okay, and the physical state is if you are dealing with gases, then your physical state is that of an ideal gas. Okay, so and if you are dealing with your liquids and solids, then you take your physical state as the real state of that species when it is at the system temperature and the pressure of 1 bar. Okay, so that is how we define the standard states. Now in this case, okay, so first of all let's see, this is the fugacity at the of the pure species in the standard state. Usually what we take is that your pressure is P naught, that is taken as 1 bar. Okay, we all know for pure species then your Fi naught that is equal to P naught and that is equal to 1 bar. Okay. Now Fi cap is the fugacity of species I in the mixture, and we have seen it that it is equal to phi I cap Yi into P. Okay, where this is your fugacity coefficient. Okay, now fugacity coefficient you can easily determine from the PVT behavior. You have seen that using the residual properties. Okay, so that's why we have kept it over here. So what you see is that fugacity is a function of composition, temperature and pressure, all 3 of them. Okay, so now I am going to put everything over here, and for simplicity's sake what we call this as your reaction equilibrium constant. Okay, so this is your equilibrium constant K. Now this equation then simplifies to product over all I. Fi cap I am going to replace it as phi I cap Yi. P fugacity Fi naught can be replaced by P naught. Whole thing is multiplied with your nu I, raised to nu I, that is equal to K. Okay, so this is the equation which I will ask you to remember. Okay, and then we are going to further simplify this equation based on what all things have been given in this problem. Okay, So now your standard state is ideal gas at 1 bar. So your pressure is P0 is 1 bar. So you can forget about it. Okay. So let's say this is 1. Now they have said that your reaction mixture, it behaves as an ideal gas. So this phi I cap, it is also unity for an ideal gas. Okay. So what you are left with is Yi into P. Again, your pressure is maintained at 1 bar. So this is also unity. Okay. So what you are left with is product over all I, Yi raised to nu I, that is equal to K. Okay. Now we are going to use this equation, but you should always remember the equation which I had asked you to, because they can change the pressure. Say for example, if they had given it as 2 bar, then you would have to put the 2 bar over here and then solve the problem accordingly. But in this case it simplifies. Okay. Now let's find out Yi in terms of the extent of reaction or the reaction coordinate. Okay. So your Yi will be given as your number of moles of I at any time divided by the total number of moles. Okay. Now Ni, how can I get? If I have Ni naught as the initial number of moles of ith component, then if I add nu I multiplied by my extent of reaction, that will give me the number of moles at any time of this component I. Okay. And what will be the total number of moles at that time? That will be equal to N0, that is the total number of moles initially charged, plus nu into epsilon, where nu is defined as summation nu I. Okay. So I am adding up all the stoichiometric coefficients. So in this case, what will be your nu? That will be equal to, for product they are positive, for reactants they are negative. So it will be 2 minus 1 equal to 1. So nu is equal to 1 in this case. Okay. So now let's write down what will be Yi's in terms of my reaction coordinates. Okay, or my extent of reaction. So let's say N2O4 first. So how many moles of N2O4 I am charging? That is 1 mole. So Ni naught, that is equal to 1. And what is nu I for that? Minus 1 into epsilon divided by, initially how many number of moles are there? 1. What is nu? Again 1 multiplied by epsilon. So this is my mole fraction of N2O4. Similarly, I can write down my mole fraction of NO2. That will be equal to initial number of moles 0, and for that nu I is equal to 2. So 2 into epsilon divided by number of moles, total number of moles. So these are my mole fractions which are given. Okay. Now if I am saying that these are my mole fractions at equilibrium, then I can equally will write it like this. This is the extent of reaction at the equilibrium. Okay. So now what I am going to do is, now I am going to put these values in this equation. Okay. And what I get is N2O4, that should be raised to minus 1, and YNO2, it should be raised to 2. Okay. So then my equation is K, that is equal to YNO2, that is raised to, okay, so 2 epsilon E upon 1 plus epsilon E, that should be whole square. And since this is raised by minus 1, so that will come in the, this is raised by minus 1, so that will come in the denominator. So I have 1 minus epsilon E upon 1 plus epsilon E. Okay. So you are with me up to this point? Fine. Now let's just simplify this, and I can write K, that is equal to, so just simplification, it will give me 4 epsilon square upon 1 minus epsilon E into 1 plus epsilon E. So A minus B into A plus B, so A square minus B square, so that's what I am using, and I am writing it as 1 minus epsilon E square. So this is the final equation which I get, from which I am going to obtain my epsilon E. But before that, I have to find out my K from the value of delta G0 that is given over here. So let's do that. Okay. So I will retain this equation on the board. Everything else I will just erase, and let's see what we get. Okay, so my K, that is equal to exponent of minus delta G0. What is delta G0? 5253 divided by RT. R is 8.314 and T is 298. So do this calculation, and what you will get is that your value is 0.12. Okay. Now put this value over here, simplify, and then we will just simplify. Okay. So that's what I am going to do is, let's first simplify this before putting the value of K. Okay. So from this equation, what I get is K times K minus K times epsilon E square, that is equal to 4 epsilon E square, or I can write that K is equal to 4 plus K epsilon E square, or I can write epsilon E, that is equal to K upon 4 plus K under root. Okay. Now this is the best time when I can put the value of K and quickly evaluate what is your extent of reaction. So you do it. It is 0.12 upon 4 plus 0.12, and your answer comes out to be 0.17. So what you find is that, and of course extent of reaction has the units of moles. Okay, so your extent of reaction is 0.17 mole. So that means that your 0.17 mole has reacted, and how much you have charged? You have charged 1 mole. Okay, so that means the fraction of N2O4 that has decomposed into NO2 is 0.17. So this is the correct answer. So this is very simple. If you see the number of calculation, the amount of calculation which you have to do is very simple, and also the equations which you are going to use are also very simple. One is this, to find out K. The other one was simply that product over all I yi raised to nu I, that is equal to K. Okay, so we are using just this equation and this equation, and you can quickly solve these this problem. Okay, so the next problem which I am going to take is based on your knowledge of ideal gases. So the second problem which we are going to take in this video is problem number 45, which appeared in GATE 2020. So in this case, let's first understand the problem, that your system is going from state L to state N via process 1, which is a single step process. And it can also go to state N via process 2, which is a two-step process. So it goes from, the system goes from L to M and then from M to N. Okay. Now in this case they have asked you to calculate what is Q1 minus Q2. What is Q1? They have said that Q1 is the net heat which is flowing into the system for process 1, and Q2 is the net heat which is flowing into the system for process 2. Okay, and you have been asked to find out the difference between Q1 minus Q2. Since it is given that this is a closed system, so we will write down first law for a closed system, and that is given as delta U is equal to Q plus W, where I am defining Q as the heat which is flowing into the system and W is the work done on the system. Okay, so that is my sign convention. Now if I am writing for process 1, I will just write it like this. For process 2, I can write delta U2 is equal to Q2 plus W2. Okay, since you are going from same point L to same point N, okay, and this is a state function, so your change in your internal energy, that is delta U1, should be equal to delta U2. Okay, so these are same, that means I can equate Q1 plus W1, that should be equal to Q2 plus W2. Or I can also write, because I want to find Q1 minus Q2, then I can write that is equal to W2 minus W1. Okay, now see over here, the gas is expanding in both the cases, so the gas is doing work, so work is done by the system. So in this case, whatever work we will calculate according to our sign convention, that will come out to be negative. Okay, since the graph is given, I am going to directly calculate my work done by finding out the area under the curve. Okay, so the work done in this process when the system goes from L to N will be the area under this total portion. Okay, so that's what I am going to calculate. Okay, so W1 that will be equal to the area under this rectangle, the area of this triangle plus the area of this rectangle. Okay, so that's what I'm going to do. But this is the work which is done by the system, so I'm going to write minus W1 over here, and let's calculate the area now. So area will be half into for this triangle, base is 0.03 minus 0.02, so 0.01 into what is the height? It is 100 multiplied by 1000, so 100 into 10 raised to 3. Okay, plus the area of this rectangle, that will be 0.01 into 100, 0.01 into 100, of course, because it is in kilopascal, so multiply by this, and the total which you get is 1500 joules. Okay, since this is minus, so W1 will be minus 1500. Okay, similarly go ahead and find this out. Again, for the process 2, the work done will be only the area which is under this curve. Okay, because this is a constant volume process, so work done will be 0 over here. So this area again I have already calculated over here. So W2, that will be given as 0.01 into 100 into 10 raised to 3. So that comes out to be, again it will be a minus W2 because work is being done by the system. Okay, so this comes out to be your 1000 joules, or W2 is equal to minus 1000 joules. Okay, now you have to find out Q1 minus Q2 is equal to W2 minus W1. So W2 is minus 1000 minus of minus 1500, so that comes out to be 500 joules. So what you get is your Q1 minus Q2, that is equal to 500 joules. That means the heat which is flowing into the system, the difference in the heat which is flowing in first process minus the heat which is flowing in the second process, that is equal to your 500 joules. So this answer is correct. So it's very simple. It just requires your first law, and when you apply, but just take care of the sign convention. Don't do it wrong. Okay, so keep in mind what sign convention you are following, and according to that, just keep that in mind. Okay, so remaining everything is fine. So if you like this video, please leave a comment so that it motivates me to make more such videos, and please don't forget to like and subscribe. Thanks for watching.